Oh, you won't be here?
Nope.
You said you won't be here? Oh.
And Grant.
Wait, you're in it too?
Wow. What, you?
Joe, I like your shirt.
What?
And Austin's sick
But
today.
did you go last time?
I'd say Austin's not here either, so it's gonna be.
Oh my god, it's gonna be me, Darren, Kylie, and you.
Hey, maybe we won't have that math class.
Yeah, because I'm the only one in math right now. Like,
Wow.
How many people is in your math class?
6.
Yeah, it's rough.
Is he like as
Mr.
fun
Brilla
as
can't hang out.
Turrington? Is
Maybe-
Turrington
Hey,
as
did
fun as
Mr. Brilla can't
Turrington?
watch that video?
No, no.
I'll make it.
Yeah, I'd say make it. Yeah. Alright, so yesterday we were having this discussion at the end of the period about, and I don't know if you were asking about this or not, but we got into the idea of quote-unquote artificial gravity, which is kind of where this is headed. So I was trying to draw something here, and then I thought about it more, and I was like, okay, I need to incrementally step you up from one to the next, okay? Alright, so we're going to start with this. Okay? So,
What happened to Hannah? She's like acting a lot recently.
it's true. She was sick last week. I don't know.
When I'm sick, no one believes me.
Sorry.
But when Hannah's sick, everyone doesn't even like say anything.
Because we like emotions.
Yeah, there we go.
Seriously?
We recognize
Okay.
patterns.
And if
I hate you.
And if Hannah's watching this, you know.
I'm really upset. The air is too clean for me to put the gas in my spot.
Dude, I love the air. I love the air. Like I wake up and I breathe.
Why
and I
is
get sick.
everybody dressed like a fascist?
Who? What's a fashion?
Am I missing it?
What's a
We
fashion?
need to watch Urban Supreme.
No.
I understand what fascism is. It's like what
I know what fascism is.
Hitler's cover style.
Oh.
Alright. So,
What does he believe?
Wage slaves.
I'll watch it.
It's 2014. Why isn't everyone taking their cocktails intravenously?
Just want to talk about artificial gravity.
Yes, I know I'm a hacker, but I prefer the term cyberspace warrior.
Am I the only one that's not getting this whole thing?
No. No, you're not the only one.
Okay, good.
So,
You don't get it either.
no,
Why are you laughing?
it's just ridiculous. That's why.
But then, because you get it, it's ridiculous.
No, it's ridiculous whether I get it or not. So,
It's fine. I'll calm down.
so.
I'll listen.
It's still ridiculous.
And I'm always calm, but like. Okay, I'll calm.
All right. So.
Look at you.
You just have to like, just kind of like shake, kind of like nod your head and be like.
No, I'm not.
So then they're just gonna keep pestering
I don't care. I'm gonna pass people back.
None of the babes in here are wearing neon spandex. It's really upsetting.
Let's stand up.
Wear the neon spandex. I'm wearing
How
neon
much longer does it take to get this all out of your system?
I don't know. I'll stop.
Wait, what's that?
I'm just.
Searching
The memes
myself.
are
Look at my
flowing.
ass.
I'm in neon spandex in the long time.
You don't even know
What's
it's
a hazing? I'm
Spandex.
searching it out right now.
Kevin, is there some left in there?
Yeah,
Is
there's
it
like
spandex
5.
with leggings?
Spandex is like
I'm searching on my
stretchy
ass.
materials. I gotta try and
Neon.
This is what our own life is.
Oh, it's like neon glowy type stuff. Same thing, like leggings, as I said. But a stretchy, like that's like soft feeling. It's kind of like reflects light. Yeah, I know what it's kind of.
Now that we
I'm out. I'm really. The other ones are lame.
Alright, you good? Okay, so, yesterday at the end of class, we started talking about this artificial gravity idea, and I want to start with this. So back 2 chapters ago, right, we talked about circular motion, centripetal force, all that fun stuff. And if we had some person standing on the inside of some big circle like this, they would need a force that points towards the middle to make them go in a circle, right? Yes, no, maybe. Good? Yeah. We talked about the idea that it doesn't matter where that force comes from, but it needs to be there. Okay? Good? Yes, no, maybe. So, let's take this same circle, let's put it above the earth, not to scale, okay? This is like the witch's wheel at Cedar Point, okay?
How big was that?
I mean, as tall as the PAC.
Just like this room.
No, like, I mean, it's the PAC. Like,
The room of the like the whole PAC?
yeah, like, you know when you stand outside and you see, like, the top of the PAC? Or maybe, like, the lights on the baseball field or something like that.
Oh, okay, okay, I know what you mean now.
It's an amusement park.
Okay.
And it just goes in a circle like this.
Alright, okay.
So, if we had a person,
Oh no.
I wanted to do it in one motion so it all stayed together, but that was perfect. So, alright. So, if we have a person, there, alright, if we have a person on the inside of the witch's wheel, there always has to be a force that points towards the middle, right? That's the gist, that's how it works, okay? And that force is always this big, okay? Good? Alright. If, as this person goes around in the circle, right, that red arrow never changes. Okay? Always the same. But we said centripetal force has to come from somewhere, right? Something has to provide it. So, let's say this red arrow, okay, and move our person, oh goodness gracious, it's not what I wanted to do. Okay. Alright, there's our red person, and this is the force that they need to go in a circle. Okay? Here on Earth, what other force is going to be pointing in that direction?
Gravity.
Gravity, right? So let's make gravity always a green arrow. If gravity is exactly as long as the red arrow, how much does the circle have to push? Nothing, right? If the gravity is just as big as the required centripetal force, the force from the circle, or like the ring, or whatever we want to call it, or the witch's wheel, is nothing. That means the normal force is nothing. So what would that person feel like, in quotation marks, up at the top? Weightless, right? Good? Okay. If, right, we move here, okay? This is still the required centripetal force, mv squared over r, right? That doesn't change. But now, what happens to gravity? It's down, right? So my green arrow is just as big as before, but now it's pointing this way. Okay? That's not going to make the person go in a circle. So what has to happen?
Oh, the circle, the spin circle.
It has to be doubled. Okay, I know that goes past the middle of the circle, but it has to be this red plus this green, because the difference has to be red. Does that make sense? Okay with that so far, right? So, then, what would the person feel like they weigh, in quotation marks? Heavy, specifically how much heavy? Twice as much, or we call that what? 2 G's, right? So this is 0G, because how much normal force is there? None. This is 2G, because the normal force is twice as big as the amount of gravity, right? Twice as big as the weight. Good so far. Okay. This red arrow is always the same, no matter what, right? It doesn't matter how big that, or where the gravity is, where the Earth is, where they're in the circle. That red arrow never changes. Okay? Good? All right. Now, let's go here. Okay? Same circle, so the red arrow is exactly the same. Okay? But we've taken the witch's wheel now, and we've moved it far off the Earth. Okay? So, if the person...
The Earth is still below, directly
Yep,
below.
Earth is still directly below, but we've taken it way off the Earth, like quote-unquote into space.
Okay.
Right? Let's say we've turned the witch's wheel into a space station.
Okay.
Okay? It's still spinning like this, right? And so the red, as long as M, V, and R are exactly the same, that red circle, or that red arrow never changes. Okay? Now that we've taken the space, or the witch's wheel, way off the surface of the Earth, what has happened to the amount of gravity that exists between the Earth and that person? It gets less. Does that make sense? Farther away you are from something, less gravity. Okay? There's still a gravitational force, but now let's say it's only that big. Okay? Does that make sense? And so, if we want to continue doing this, we need more force. Where's the force going to come from? Even though we're out in the middle of space, right? We still have what? Well, no. Centripetal force is the red one. That never changes, right? Even though we're in space, the witch's wheel is still there, right? All right? You're still sitting in that seat. So, can there be a normal force acting on you? Yeah, there can be. Doesn't matter that we're not on Earth anymore. We think of normal force a lot of times as being the force that opposes gravity, but really it's just a force that comes from a surface. Okay? So in this case, if we had a normal force that was this big, plus green, blue plus green equals red, right? That make sense? Okay? So here, even though we're way, way, way far away from the Earth, it would still be 0.75 G. Does that make sense? Where those numbers came from?
It's not weightless.
It's not weightless, right? Because remember, when we talk about quote-unquote weightless, right, it's not gravity, it's normal force. Okay? So here, would you feel like you feel on Earth? No. But would you still feel like you're quote-unquote way something.
Yeah.
Yeah. Okay? Alright. Good so far? Well, so let's do that, okay? So, Joe, here, we'll do this, okay? Okay. Let's take this and let's get rid of Earth, okay? Okay, no more Earth, right? How does that change the picture? There's no green arrow, okay? But I still want to go in a circle, okay? Will I go in a circle with this? No. There needs to be a combination of colored arrows that gets me to red, right? So, we talked about that normal force, the force from the floor, depends on what else is going on, right? Here, the floor is pushing up on me equal to the amount that gravity is pulling down on me. Now the floor is pushing up harder on me. Does that make sense? Right? The floor can change what it does based on what else is happening. If I put too many books on my head, right, eventually I could fall through the floor, right? Because the floor just can't push enough up. I suppose. So, if that blue arrow increases, right, now this goes from 0.75 G to 1 G. Okay? Enjoy. Maybe they'll let you go outside today, like down by the pond. That would be pretty cool. So I say if you go outside by the pond, that'll be so. Okay.
Why is it 1G instead of 2G?
Well, going back to this original picture, okay? This red arrow, we calculate with this formula, right? Okay? The mass of this person, how fast it's going around the circle, and what the radius of this circle is. Okay? As long as we don't change any three of these things, that red arrow is exactly the same length in every single picture we've drawn so far. Because it doesn't depend on where we are or where the force comes from. All that matters is the mass of that person, how fast they're going around a circle, and what the radius of that circle is. Okay? The amount of centripetal force doesn't depend on where it comes from. It depends on the circle that we're making. Okay? Good there?
So what if you jump and land it?
Let's not go there yet. Hold on. Hold on. Right? So, here, nope, not here. Right? So, that red arrow is exactly the same every single time. Here, because gravity is exactly the same value as the red arrow, the normal force, which is blue, doesn't have to do anything. That's why it's 0G. Here, because gravity's pointing away, the normal force has to work twice as hard. That's 2G. Okay? Sorry, back up. Okay? Let's say just per chance, our mv squared over r was exactly the same value as 9.81 times m. Okay? Whatever your mass is. Okay? So v squared over r, we spun the witch's wheel had exactly a speed and its radius was just as much, that the combination of mv squared over, v squared over r was 9.81. So the centripetal force is m times 9.81. You follow me? Okay. That's just per chance. Okay. And 9.81 is an important value to us, right? Because of Earth's gravity. Okay. So that means here, red is still 9.81 m. It just so happens that green is 9.81 m in this situation as well, because that's what Earth's gravity does to us, right? No, but why couldn't? That's exactly the same.
Polypop? Let me. Wait. Powder. Oh wait. Okay. Powder puff.
What?
Oh my god, who's in
It's like
Powerpuff?
boys doing
Someone
girls
signed me up
things.
for it. Like, literally, I didn't even sign up. Grant was gonna sign me up.
Why did you done it? Alright. So here, red is still 9.81 m. Green is still 9.81 m, but it points the wrong way, and so that's why blue has to be twice as big. Does that make sense? Okay. Here, red is still 9.81 m. If there's no gravity, blue will have to also be a value of 9.81 m. Does that make sense? So it feels like, quote unquote, 1G. Is there any gravity actually acting on you? Is there any green arrow in that picture? Right? But because the normal force is 9.81 m, what would it feel like to you? Feel like this. If you were on the edge of that circle that was spinning around at just the right speed, just the right radius, it would feel exactly like home. You would, alright, you're doing all this, it would feel that same way to you. Okay? Now, does that make sense? Alright? And if, let's say, you had a ball, right, and you dropped it, okay, let it go. It would try to go, let's go purple for the ball, right? So there's the ball, okay? As long as it's in your hand, it goes around in the circle with you, right? But if you let it go, what does it try to do? What did we say things that are traveling in circles try to do? Go straight, right? But if it tries to go straight, where does it eventually end up? The wall, which, as far as you're concerned, is what? The ground. Does that make sense? Because if you're standing on the inside of that circle that's underneath you, it feels and looks just like the ground to you.
So like, if you drop it as you spin the spot on the floor where you are, is where the ball will hit. So it'll look normal.
Yep.
Oh.
Does that make sense? Oh. All right. So is that good so far? Okay.
I'll lose it like tomorrow because.
That's like if you watch science fiction films, that's what you do, like to make quote unquote artificial gravity. Is there any gravity in this picture? No. But can you tell the difference? No.
So if you jump, it's exactly.
Yep, because if you jumped, the floor wouldn't be making you go in a circle anymore, right? No. You would go in a straight line. But if you go in a straight line, right, so you jump, right, you leave the surface of the wall, but that would take you here. And eventually, where would you end up? On the ground, or the quote-unquote ground. Does that make sense?
Yeah.
Devin, go ahead.
What happens if the balls like stay up? Like because of the
So, it would try to go this way, right? So, ball, sorry, purple. It would try to go this way, and inertia would take it that way, but it's also still trying to do what? Go straight. Does that make sense? Okay. Good so far. On Earth. Well, see, on Earth, this doesn't quite work because we always have that big green arrow pointing downward no matter where we are. That's why the witch's wheel works, because when you go down the bottom, it feels like, you're getting pushed into the seat, and when you go over the top, it feels like nothing, right? And that's fun, because you get up that change in normal force, right? That's what a ride is.
Oh, that's why I hate it.
So you feel like you're gonna puke.
Yeah, these are like you're gonna puke.
Yeah,
So
exactly.
it's a ride at Cedar Point. So you
More
sit.
fun if you look
I'm not a fan.
at all the scenery
Yeah,
spinning
not a fan
around you,
either.
Right.
and then move your head really fast. Yeah, that's great. That's a good thing. And talk.
Okay.
Everyone behind.
So now let's go here. Okay. This is orbit, right? Okay. Person, International Space Station. There's a floor on the International Space Station, but when we bring the Earth back into the picture, what shows back up in the picture? Gravity, green arrow, right? If the green arrow is just as big as the red arrow, right? What does it feel like? Nothing. 0 G. That's why astronauts in the space station float, in quotation marks, right? They float because there's no normal force. There doesn't have to be a normal force because gravity's there, right? Does that make sense? Same thing, right? Man, I want to go there. All right, are we ready to make the jump? Say again?
What jump? Scare me.
Well, okay.
Too sweet. It's such
Okay. Here's you on the space station.
Me?
Okay. Here's gravity. Okay. Here's the moon. Okay. It's the same thing for the moon, right? The moon, if we asked the moon, right, it would be quote unquote weightless. Does that make sense? Okay. All right. Now we're ready to make the jump. Good. Do we need any questions to get out of our system?
Why is the moon getting negative left if it's gravity?
Remember we talked about that red arrow for centripetal force makes a perfect circle as long as we're going the correct speed, the correct distance, and all that stuff. If we're not going that correct speed, now we start going elliptical. Does that make sense? All right. Deep breath. Okay. Here we go. General relativity. Yeah. All right. So, Einstein is not happy with his theory because, and I think we explained this yesterday, it only applies to cases of constant velocity. The question, and this is not necessarily Einstein's question, but remember the cliffhanger question that I left you with the one day before we got into relativity? Yeah, like
Those
2 weeks
black
ago.
holes.
The black holes, right?
Yeah, it's like in the
Light doesn't have mass, but it still gets sucked in the black hole. We still haven't answered that question.
I know.
Okay? We talked about all these weird things with the speed of light and how that messes with time and all that stuff, but it still doesn't answer the question of how does light get sucked into a black hole. So, Einstein keeps working on it. In 1905, he puts out his theory of special relativity. That's the first part, stuff we've been doing for the last week. In 1913, I think it's 1913, he puts out his theory of general relativity. Special relativity is special because it only applies to special cases, like constant velocity, inertial frames of reference. General relativity applies to everything. Acceleration, constant velocity, doesn't matter. And here's how it starts. All right, so, ready? Wham. Okay? So, we've done this, right, 100 times so far this year, maybe 1,000. Yes? Oh, no.
Oh no.
What?
1,000 alone.
Oh, yeah, 1,000 alone in this chapter, maybe, right? So,
Oh my God.
we drop the ball, it falls to the ground.
Yes,
Okay?
yes.
And there's a ton of explanations for why it happens, okay? If we talk about it from an energy standpoint, potential energy into kinetic, or if we talk about how it happens, the first answer you would say is, well, how does that happen? First answer is gravity, right? And that's what Newton said. Gravity will pull things together, mutual attraction. But we still have the problem, how does gravity work? Why is there a mutual attraction? And Einstein said, maybe there isn't. And this is what he said. So, you let this ball go, it accelerates as it moves towards the floor till it hits the floor. Okay? If there was no gravity and I let the ball go, what would it do? It would just stay there, right? Inertia. Okay? Okay. Deep breath.
Scare me. Can I stay
Okay. What if there was no such thing as gravity, but this room was actually accelerating upward at a rate of 9.81 meters per second squared?
I know.
It would make it
I
feel
know
exactly the same way.
Tell you my
And if I dropped this ball,
It's
no.
Not, it's not that moving. It's
it
not
wouldn't
moving.
go down at that same rate. What does it do when I let it go? It just stays there. But what is the floor doing?
Going up.
Going upward at 9.81 meters per second squared. So what would it look like?
It's dropping.
If this
The floor
room,
is dropping against it.
if this room, all right, now wait a second. That's actually the easy part, all right? So then this is the last section of the easy part, which is the middle picture there, okay? So if the room was if the room was moving upward at a constant velocity, but not accelerating, and I let the ball go, what would it do? It would stay there. It's moving upward at a constant velocity.
The floor is,
The
right?
room is moving, right now, if this room was moving upward at a constant velocity,
Everything is moving
every
up.
moving is upward at a constant velocity. So even if I let this go, inertia says what?
It's gonna stay, but it's
Well,
gonna,
inertia says
it's
it's going to keep going. But if it keeps going at exactly the same rate as me and the floor, where does
Oh,
it stay?
shoot.
Right in the middle, right where it was.
Okay.
Okay.
Wait, so is he saying that like that happens because like the universe is expanding?
What he's saying is that there is no difference between gravity and acceleration. What Newton said was gravity causes acceleration. But what Einstein is saying is gravity is acceleration. Does that make sense? Okay? All right. So, It stands to reason then. Okay? So are we good with these three pictures right here? Okay?
Wait.
These are the first three pictures that you have in your packet, right? Here on Earth, if you're in an elevator, okay, this is Einstein's like, you know, thing. So if you're in an elevator with no windows or doors, you can't see the outside. If you let the ball go, it ends up on the floor. But is it because gravity pulled it down, or is it because the room went up? And the answer is, you can't tell. Exactly the same thing. Okay? Just like this, right? Okay? Now, here's where it gets a little trickier. So, flashlight, okay? If I take this flashlight, right, and shine it across the room, I wish I had a laser pointer.
Wait, don't tell me that's real.
But I don't. Here's what Einstein says. All right, let's go first with the theory. Remember, theory is an explanation, right? We still don't have an answer for how light gets pulled into a black hole, right? Because it shouldn't.
Oh my god,
The
black
effect-
holes fall into the light?
No, light is
Okay,
falling
good,
into
good,
the black
okay,
hole.
good, okay, continue.
All right, so if I had a laser pointer, let's pretend it's a laser pointer, right? Shine it across the room, boom. It hits the wall on the other side. This isn't a laser pointer, but if I had a laser pointer, right? Okay. If I had a laser pointer, it would shoot across the room, and it hits the wall. Where? Directly across the room from where I shot it, right? Okay. But that's contrary to what would happen if I threw the ball across the room, right? If I threw the ball across the room, it wouldn't hit the wall directly across where I threw it from. It would curve downward. Einstein said you can't do that. You can't have different rules for light and matter. Okay? If you were in an elevator that was traveling upwards at a constant acceleration, when you shine the light and it leaves whatever source that's producing it, it would go in a straight line because of inertia. But what is the room doing? Going upward. So will the light hit the wall directly across from where I shot it from? Nope.
Wait,
It's
it's seriously,
From where I shot it from. Does that make sense?
It makes sense, but like,
Okay.
it doesn't have.
Does it really not make sense? Or do you just not like it? Okay. Do you understand the concept?
Yeah.
Or what the picture's of, right?
So good.
Okay. So, end story, right? Or the big revelation that comes out of this is gravity can actually bend light. And gravity affects light.
It's acceleration now.
But what Einstein says is it any different?
How does the bend light where it doesn't have any mass?
That's where he's getting at. Like, okay, well, if black holes exist, and at the time we didn't know, Einstein really didn't know about black holes because we hadn't really figured them out. But say again?
When he knew that light was gonna
No, we hadn't identified black holes yet. Okay. No, he didn't even know that, right? He's just working under the premise of, okay, wait a second, I gotta figure out how this works. Light can't behave differently at a constant velocity than it does at an acceleration. The rules can't change whether you're moving faster or slower or not moving at all. It's gotta be the same rules.
So sweet. So light doesn't go at a constant velocity then?
Light does go at a constant velocity,
But it's changing.
but it's changing direction.
So that means it's accelerating.
It's accelerating,
But
right?
it's not changing speed.
It's not changing speed, which can happen, right?
Yeah.
Things can accelerate and not change speed. But more importantly, for our consequences here, right? If this would happen in an accelerating elevator upwards, it would also have to happen in what we classify as a gravitational field. Because according to the other experiment with the ball, you can't tell the difference between a gravitational field and an accelerating field, or an accelerating frame of reference. Does that make sense? For starters? Okay. So, now we've taken our first step into the bigger world of general relativity. Right? And hopefully by the end of tomorrow, we'll talk about how black holes actually work, and why we get these things out there, and then some other consequences. Okay?
What is it?
It doesn't. So the question, so Hannah's question was, why it still doesn't have mass. And what Einstein is saying is that gravity isn't a force that exists between two masses. That's not what gravity is. Even though that's what Newton said it was, Newton was just not equipped experimentally to handle what gravity actually is. Okay?
So black holes have mass, but how? What are they?
They're matter. But it's not so much what they are, it's what they do to the stuff around them.